In this video, I'll be talking about method of lines, which is applicable to the second problem in homework 7. So in method of lines, we're going to look at a generic equation as the heat equation. That is du dt or d theta equals d squared u dx squared. So this is the diffusion equation, or you can also call it heat equation. So imagine we have three boundary conditions. At x equals 0, we have u equals 0. At x equals 1, we have u equal 1. And then at all x values, when t is equal to 0, which is the initial condition, u is 1. So the first two are boundary conditions because it's on x values when x is 0 and x is 1. And the last one is the initial, which is about when time is 0. So in some sense, method of lines is very similar to the finite differencing method. It also very similar to Crank-Nicolson, but there is one difference between method of lines and Crank-Nicolson, and that is in Crank-Nicolson, we apply finite differencing method on both sides, on the left side and on the right side. But in method of lines, we only apply the finite differencing method only on the right side. So that is to say, if I want to discretize this diffusion equation, on the left side I get du I dt if I center both sides at point I. And on the right side, I get the central differencing centered at I, which is ui minus 1 minus 2ui plus ui plus 1 divided by del x squared, where I varies from 1, 2, all the way to n. So this is akin to an x-axis on which I have n plus 2 points. The first and the last point are boundary points, and then I have n intermediate points from x1 all the way to xn. Once again, x0 and x plus 1 are the boundary points. This is to say I have n plus 2 u values as well. u0 is the boundary point on the left, u1 through un are the intermediate points, and then the last point on the right side of the boundary is un plus 1. In the case that we're looking at, because u0 at all time is 0, that means u0 is 0. u1 at all time is equal to 1. That means un plus 1 is 1. And the only condition that is left to be seen is ux at t equals 0 is 1. So we cannot show it on this figure. This is all about u values and the boundary points. It's not about initial value. So let's get back to our equation. We discretize the right side of the heat equation, and we didn't discretize actually the left side. So the left side still is d dt. But then this u is ui because we centered both sides at point I. Now, let's go ahead and plug in I equal 1. So if you plug in I equal 1 in this equation, on the left side you get du1 dt. On the right side you get u0 minus 2u1 plus u2. This is exactly shown here. Now we know that u0 is 0 because on the left side, on the left boundary, u is 0. So we can apply it right here. So this is simplified to minus 2u1 plus u2. The first term is gone. Now when we plug I equal 2 in here, the left side becomes dut dt, and the right side becomes u1 minus 2u2 plus u3 divided by del x squared. Again, I'm replacing all I values here by I equal 2. Okay? So we can keep doing this with I equal 3, 4, 5, all the way to let's say when I is n minus 1. When I is n minus 1, the left side becomes du n minus 1 over dt, shown here, equals to, and on the right side, when I is n minus 1, you get un minus 2 minus 2un minus 1 plus un divided by del x squared. And now the last value is when I is equal to n, and that is to say u dun dt is equal to un minus 1 minus 2un plus un plus 1 divided by del x squared. So now here we can also use the second boundary condition on the right, which is u at x equal 1 and all time is 1. So I can use that value here. So let's rewrite these n equations from I1 to all the way to n, I equal n. Let's rewrite these n equations in a matrix form. So let me go to next page. This is the matrix form of the same n equations. There is no difference between these equations and the one on the previous page. The only thing is I just rewrote those equations in a matrix form. So d dt of now a vector of all u's from 1 to n is equal to, I factor out 1 over del x squared, and here's all u's on the right. So from chapter 6, if you recall, if I represent the left side by vector y vector with arrow on top, and then the right side by right hand side or RHS with vector on top, I can rewrite this equation as dy arrow dt is equal to right hand side. Now let's apply forward Euler to this to this first order differential equation. So we're going to use forward Euler to this equation. So from chapter 6, we saw that we can easily write this as yn plus 1 is equal to yn plus del t right hand side at point n. So from now on, all the technique we learned in chapter 6 can be applied to solve this system. So in the next video, I'm going to show you how we can implement this in VBA, which is example 8.5 of the textbook. One point to keep in mind is, instead of forward Euler, I can apply, let's say, Runge-Kutta 4. If I want to do that, then I have to calculate 4 k values for Runge-Kutta, k1, k2, k3, k4, which if you refer to, I guess, chapter 4 or 5, you can see that k1 is del t right hand side evaluated at yn, k2 is del t right hand side evaluated at yn plus half of k1, and then time is equal to tn plus, well, this should be del t over 2. I have del x, so it's a typo here. It should be del t over 2. K3 is del t right hand side evaluated at yn plus k2 over 2, and time equal to tn plus del t over 2. Again, there's a typo. This should be del t over 2. And then k4 is del t right hand side at yn plus k3, which we calculated before, and time equal tn plus del t. So all these should be del t instead of del x. After calculating all these 4 k values or k vectors, now we can calculate yn plus 1, which is yn plus the weighted average of k1 to k4. That is to say 1 over 6, k1 plus 2k2 plus 2k3 plus k4. Okay, so this is the Runge-Kutta 4 version of solving this system, and this one is the forward Euler version of the same equation. So let's go back and see if we change the boundary condition, what happens to our system of equation. So the boundary condition we look at was 0 on the left side, 1 on the right side, and the initial condition was 1 for every x values. Now let's change the right side boundary condition, this middle term over here, to du dx equals 0 at x equal 1. So let's see if I change that boundary condition, if I change this boundary condition to du dx at x equal 1 equal to 0, how I should modify the system of equation. So let's use our old technique of backward difference on this boundary condition. So from page 83, or from problem 1 of the same homework, you realize that the backward difference version of this can be written as, well, this is written for the last boundary point right here. So that condition can be discretized to 3n un plus 1, which is the last point, minus 4 times the point before, which is un, plus un minus 1, which is the point right before un. So this is the backward difference discretization of du dx at x equal 1. We set this to 0 because the boundary condition said so, and by doing so, we can actually equate the numerator to 0, and from here we can solve for un plus 1. So un plus 1 is nothing but 4/3 of un minus 1/3 of un minus 1. Basically, you just take these two to the right side and divide through by 3. Now all you need to do is, in the last equation of your system of equation, before we had un plus 1 equal to 1, now you have to plug in equation 1 right there. Now if you do that, you see that the last equation becomes du and dt equals un minus 1, same as before, minus 2un, nothing has changed so far. Now plus, instead of un plus 1, I have this term, which is 4/3 un minus 1/3 un minus 1. Now I can group un and un minus 1. That is to say, 1 minus 1/3 times un minus 1, which is 2/3, times un minus 1, minus 2 from this term, minus 4/3 from that term. So together becomes 2 minus 4/3 un, which is 2/3 times un. Well, I haven't simplified that, but you can do that. So this is your last equation. All you need to do is change the last equation to this one. And then you can go ahead and use the same techniques, either Runge-Kutta 4 or Fowler-Euler, to solve the problem. So now in the next video, I'm going to show you how we can implement this in VBA. Thanks a lot for watching.